A uniform rod of mass 3 kg is hinged at the wall and connected to a light string as shown in the figure. Find the tension in the string. The options are 30 Newton, 15 Newton, 5 Newton and 10 Newton. First, let us identify all the forces acting on the rod. So let's do that. So here is our system. So let's identify all the forces one by one. Well, there is the tension in the string acting along the length of the string. There is this contact between the rod and the wall at the hinge. So there will be the normal reaction at the hinge. Vertical, I'll call it as Ny. Horizontal, I'll call it as Nx. Will there be a horizontal normal force? Let us see. What is also acting is the weight of the rod, mg, right at its center. So if L is the length of the rod, then this part length will be L by 2. So this will also be L by 2. What are we supposed to find out? We are supposed to find out the tension in the string. Now, the rod is in equilibrium. And whenever a system is in equilibrium, two important conditions must hold good. First one, the vector sum of all the forces acting on the system must be 0, which translates into summation fx is equal to 0, summation fy is equal to 0 and summation fz is equal to 0. But most of the problems that we do are two-dimensional. So we have considered this as x and this direction as y. So what is summation fx is equal to 0 giving you? Well, summation fx is equal to 0 will give you nx is equal to 0. No other force is along the horizontal, that is the x direction, isn't it? What is summation fy is equal to 0 giving you? Well, the upward forces are ny plus t and the downward force is mg. So ny plus t minus mg must be equal to 0 or ny plus t must be equal to mg. Well, we are supposed to solve for t, agreed? But there is this ny that we don't know, the reaction force at the hinge. For that, we're going to go for net torque about any axis must be equal to 0, the second equilibrium condition, right? Net force must be 0, net torque about any reference axis must be 0. Now what I'm going to do is, since I want t, right, I'm going to take the axis at O, the hinge, such that ny doesn't have a torque at all. So let's do that. So I will say summation torque about O must be equal to 0. So about O, nx and ny won't have a torque. Nx is already 0, so you don't have to worry. Ny is passing through O, so it does not have a torque, because torque or moment of force is what? Force times perpendicular distance. Now ny is passing through O. So what are the perpendicular distance between ny and the axis? 0. Right? Now this perpendicular distance, you can clearly see, is L by 2 sine theta, and this perpendicular distance is L sine theta. So we know the perpendicular distance of tension from the axis, which is L sine theta, and perpendicular distance of mg from the axis, which is L by 2 sine theta. Now as far as O is concerned, mg is acting downwards, so mg is trying to produce a clockwise torque, and as far as O is concerned and tension is considered, so T is making it rotate anti-clockwise. So summation torque about O is equal to 0 will now become mg into its perpendicular distance, which is L by 2 sine theta, with a minus sign, because the usual convention is clockwise is negative, anti-clockwise is positive, plus tension will have an anti-clockwise torque. So T into L sine theta must be equal to 0. Now let us solve it here. So I'll have TL sine theta must be equal to mg L by 2 sine theta. Sine theta gets cancelled, L gets cancelled, T becomes mg by 2. What is m? M was 3 kg, so 3 into g, 30 by 2, which is 15 Newton, and that, my dear students, is the required answer for this particular question. We used the idea of equilibrium. Net force must be 0. Vector sum of all the forces acting on the system must be 0, and net torque about any given reference point must be equal to 0. So all the equilibrium problems can easily be solved by using these two conditions, which are the required necessary conditions for any system to be in equilibrium. Correct? So what is the answer we have obtained? T is equal to 15 Newton. And which is the option that supports our answer? Well, it is option B. A block of mass m is equal to 50 kg, base B is equal to 1 meter and height h is equal to 3 meter is kept on a rough inclined surface with coefficient of static friction mu is equal to 0.8 as shown in the figure. The angle of inclination with the horizontal is 37 degrees, that is the angle of the incline. Determine whether the block slides down or topples over. Here is the diagram and here are the options. It slides down, it topples over, it remains in complete equilibrium, cannot be determined. So let us see which one of them is the correct one. Here is our system. Now when will this block slide over? Well, it will start sliding over when mg sine theta, which is the force or the component of weight acting along the incline, exceeds the limiting friction. That's when it just starts sliding over or sliding down the incline. When will it topple? Well, the normal reaction keeps on shifting its point of action so that it can provide the torque required to balance the torque of mg sine theta, and it keeps on increasing as you keep on increasing the angle theta. What keeps on increasing? The value of x. And until when can it increase? Well, it can increase until this normal reaction reaches the edge, after which it cannot shift its point of action and hence the block will topple over the edge once this condition is reached. Now we will have to see whether any of these conditions have been reached or they are yet to reach, and depending on the answer that we get, we'll have to select the most appropriate option. Correct? So let us start. Let us identify the forces acting on the block. Well, one component of mg, which is mg sine theta, is acting parallel to the incline. The other component is mg cos theta, is acting perpendicular to the incline. Of course, there is this normal reaction which has shifted by an amount x, let us say. Why it has shifted, you will come to know. And what prevents the block from sliding is the frictional force acting, right, up the incline, which is trying to balance mg sine theta. So considering this as x-axis, this as y-axis, assuming the system is in equilibrium, I must have summation fx is equal to 0, which implies which are the forces acting along the x-axis. Well, it is mg sine theta and f. So mg sine theta is in one direction, f is in the opposite direction. So these forces must balance each other. So mg sine theta must be equal to f, and summation fy is equal to 0 will imply n must balance mg cos theta, isn't it? So this is the equilibrium conditions as far as the force is concerned, assuming the block is in equilibrium. If it is, let us see. Okay. Now, once you do this, when will sliding occur? Well, the block will just about to slide down the incline when limiting friction is reached. That is, when theta has been increased in such a way such that mg sine theta will be equal to FL, the force of limiting friction, which can be written as mu times n, and n is what? Mg cos theta. So mg can be cancelled, so you'll get tan theta is equal to mu, and from the problem, remember, mu was given to be 0.8, right? So tan theta is mu, which is 0.8. In this case, right, theta is 37, and let's quickly calculate what is tan 37. Tan 37 is 3 by 4, which is basically 0.75. So tan 37 is less than tan theta here, or 37 degrees is less than theta, the angle for which sliding will occur. We call it as the angle of repose, remember? So 37 degrees is less than theta, so definitely the block has not yet begun to slide. No sliding is occurring. So as far as the sliding part is concerned, it is still in equilibrium. Static friction is still acting. Limiting friction has not been reached. Limiting friction will be reached only when theta is such that tan theta is 0.8. Now for 37 degrees, tan 37 is 0.75. So sliding is not happening. Now let's check for toppling. Now as far as toppling is concerned, I'm going to consider this point O here, and since it is still in equilibrium, as long as it's just about to topple, I will say torque about O must be equal to 0, because we are assuming that even if it is toppling, it is just about to topple. So let us see that. So torque about O must be equal to 0. The net torque about O must be equal to 0. Now as far as O is concerned, you can clearly see that the frictional force is passing through O. It will not have any torque. Mg cos theta is passing through O. It will not have any torque. Mg sin theta is at a perpendicular distance of h by 2 from O. And n is at a perpendicular distance of x from O. So these are the only two torques, and as far as mg sin theta is concerned, it is making the block go anti-clockwise, and as far as n is concerned, it is making the block go clockwise. So I will have mg sin theta into h by 2 with positive value. Why? Because anti-clockwise torque, and minus n into x with a negative value. Why? Clockwise moment or clockwise torque must be equal to 0. Now let us write it down. So mg sin theta into h by 2 will be equal to n. N is mg cos theta. Remember, mg cos theta into x. Mg gets cancelled. Now we'll have tan theta is equal to 2x by h. 2x by h. Now what is the maximum angle for which toppling will happen? If I call that angle as tan theta t, theta t is the maximum angle for which toppling will happen. That will be equal to 2 by h. H is given to be 3 here, into x max. Right? As x increases, tan theta keeps on increasing, isn't it? That's the logic. So what is x max? The maximum value x can take is it can go up to this length, which is b by 2. B is given to be 1 meter. So b by 2 will be half. So this will cancel. So you will have tan theta t equal to 1 by 3, which is 0.33. What is the angle now? 37 degrees. And what is tan 37? 0.75. So definitely 37 degrees is greater than the maximum angle at which toppling would have happened. 100%. So before you reach 37 degrees itself, the condition for toppling would have been reached. So the moment you place the block on this particular incline at 37 degrees, it will immediately topple. Immediately it will topple, and that's the required answer, my friends. The block will topple over. And which is the option that matches with our result? Well, it is option B. A thin uniform rod of length 3 meter and mass capital M is held horizontally by two vertical strings attached to the two ends as shown in the figure. One of the strings is cut. Find the angular acceleration of the rod at that particular instant. Take G is equal to 10 meter per second square. So the rod is in equilibrium held by two identical strings, and one of them, any one of them, let's say, is cut. And what will happen the moment you cut it is that the rod will begin to rotate about the other string, right? Let's say this is point A and it will start rotating about that, and we want as to the moment the string is cut, what is the angular acceleration of the rod. So all we have to do is write the torque equation, which says net torque is equal to I into alpha, where I is the moment of inertia of the rod about the rotational axis here, and here we can clearly see that it is rotating about one of its end point, and if it is rotating about one of its end point, what is the moment of inertia? It is ml squared by 3, remember. So now all we have to do is the moment one of the string is cut, find out the net torque about A, let's say one of the ends, and then use net torque is equal to I into alpha, substitute the values and solve for alpha. Let us do that. Before that, let us see the options first. Well, here are the options. Option A 15 radian per second square, option B 10 radian per second square, option C 5 radian per second square, and option D 7.5 radian per second squared. Now let us see as to exactly what happens in this scenario, right? So here is the rod. Let's say you bring in a knife and cut it. One of the strings is cut, and the rod, as I told you, will start rotating about the other end, and at the instant it just begins to rotate, we have to calculate as to what is the angular acceleration the moment, the instant the string is cut. Let's identify the forces acting the moment the string is cut. Well, of course, there will be the tension in the string here, T. The other string just vanishes, and mg is acting vertically down as always. So these are the only two forces, and I want alpha. So instead of calculating net force, I would like to calculate net torque. About which point? Well, about A would be very beneficial for me, because then T will not have any torque. I don't know the value of tension, isn't it? So but if I choose A as my reference point for finding the net torque, T is passing through A, so it will not have any torque. So all I'm gonna use is say net torque acting on the system with respect to point A must be equal to moment of inertia of the rod with respect to the point A into alpha. Alpha is what we are after, that value. What is the torque about A? Well, torque about A is T does not have any torque, and the perpendicular distance of mg is nothing but L by 2, half the length of the rod, isn't it? So it is mg into perpendicular distance, which is L by 2, is equal to IA, moment of inertia of the rod about the point A, which is an end point. Well, you should know this value. It is ml squared by 3 into alpha. Is the value of m given in the problem? No, sir. No problem. That is exactly why they haven't given, because it gets cancelled. And what is alpha? Alpha will be 3gl by 2l squared. I can cancel 1l. It is 3g divided by 2l. That's the required answer. And you have 3 into g is supposed to be taken as 10 divided by 2 into L. What is L? Well, L is 3 meters. Agreed? So you will have 10 by 2, which is 5 radian per second squared, and that, my students, is the required answer for this particular question. Since alpha is asked, all we used was the torque equation, and from that we calculated alpha to be what? 5 radian per second squared. That's the required answer. And which is the option that supports our answer? Well, it is option C. A thin rod Mn, free to rotate in the vertical plane about the fixed end N, is held in a horizontal position. If the rod is released from this position, speed of end M when the rod makes an angle alpha with the horizontal will be proportional to. And the options are option A, root of cos alpha, option B, sine alpha, option C, root of sine alpha, and option D, cos alpha. Well, let us see how to handle this question. So as soon as the end N is held and M is released, the rod will begin to rotate about N. Correct? The rod will begin to rotate about N, and when it makes an angle alpha with the horizontal, this will be the final position of the rod. And what is the logic there? Well, the center of mass of the rod has moved below its original position. So if I take this as the initial state, this as the final state, the center of mass has come down, which means the gravitational potential energy of the rod is decreasing. And where is that decreased energy going into? Well, it is going into the kinetic energy of rotation of the rod about N. So at this position, if I call omega as the angular velocity of the rod about an axis passing through the fixed end N, then half I omega squared will be the kinetic energy of the rod. What is I? The moment of inertia of the rod about the axis passing through N, which is an end point of the rod, and it will be ml squared by 3. Got it? So now we can write Ki plus Ui is equal to Kf plus Uf. Now you might ask as to the fact that there will be some external forces at the hinge, the point of pivot, that is point N. Though there are forces here, external forces at point N, and we are looking at a pure rotational motion of the rod, that is rotation about the axis passing through N, these external forces will not have torque because we are calculating the torque with respect to the point N. These forces are passing through N and hence will not have any torque. If they do not possess torque, a moment of force, they will not perform any work. So there won't be W external. So you will have mechanical energy conserved. In this case, Ki plus Ui is equal to Kf plus Uf. What is Ki? The initial kinetic energy of the rod, and it is released from rest. So Ki is 0. What is Ui? Initial gravitational potential energy of the rod. It is at the horizontal position, and that itself will be considered as the datum or the reference for gravitational potential energy. So Ui is also 0. So I'll write it here. So LHS is 0. What about RHS? Kf is the final kinetic energy of the rod at the position indicated in the diagram. So that is half I omega square. And what about Uf? Well, from the datum, the reference point has the center of mass moved down or up. It's moved down. So we have to consider the gravitational potential energy as negative. And what will that be? It will be mg. Whatever is the height, it has gone down. This length is L by 2, isn't it? So this length is L by 2. This is alpha. You can clearly see that this length will be L by 2 sine alpha, and this is the distance by which the center of mass of the rod has moved down from the reference level. So that is the height. I'm going to use L by 2 sine alpha. Now let's solve for omega. So I'll have half I we have already discussed, ml squared by 3. Omega squared must be equal to, take the negative term to the other side and it will become positive. So that will be mg L by 2 sine alpha. M gets cancelled, 1 L gets cancelled, 2 gets cancelled. So from this I'll have omega squared is equal to 3G by L sine alpha, or omega is square root of 3G by L sine alpha. So it is very clear from this that omega is directly proportional to sine alpha under root. What does the problem asks for? Well, it is asking for the velocity of point M, which is going in a circle of radius L, and since Vm is the tangential velocity, we can write V is equal to R omega. And what is the radius of the circle as taken by M? It is L, the length of the rod. So velocity of M is equal to L omega, which implies velocity of M is proportional to omega, and since omega is proportional to root of sine alpha, velocity of M will also be proportional to square root of sine alpha. That is the required answer for this particular question. Vm is proportional to root of sine alpha, and which is the option that matches with our result? Well, it is option C. A long uniform beam is acted upon by several forces as shown in the figure and is in complete equilibrium. What will be the values of forces X and Y? Neglect the mass of the beam. So we don't have to worry about the weight of the beam, which is M into G, where M is the mass, because they have asked us to calculate or to neglect the mass of the beam and calculate the values of X and Y. So X is a force acting downwards, Y is a force acting upwards, plus there is a 6 Newton force acting up and a 6 Newton force acting down. And if this beam is in equilibrium, what are the values of X and Y? That is what is asked for, and here are the options. X is equal to 3 Newton, Y is equal to 3 Newton, X is equal to 0, Y is equal to 6, X is equal to 6 Newton, Y is equal to 3 Newton, and X is equal to 6 Newton and Y is equal to 6 Newton. Let us see which one of these options turns out to be the correct one at the end. Let's consider the diagram. Well, here is the beam, massless beam, because mass is supposed to be neglected, in equilibrium. So if a system is in equilibrium, net force on it must be equal to 0 and net torque about any reference point must be equal to 0. Two conditions to be satisfied for any system to remain in equilibrium, isn't it? Well, considering this as y-axis and this as x-axis, it is very easy to see that there are no forces along x-axis in this particular situation. So I'm going to use summation Fy is equal to 0 here, which implies x is downward, so I'll write it as minus x, y is upward, so I'll write it as plus y. This 6 Newton force is upward, so plus 6, and this is downward, so minus 6 is equal to 0. Plus 6 and minus 6 will cancel out, and I'll get x is equal to y. So the magnitudes of x and y are equal. Got it? But we still need to know equal to what value. For that, I will go for the torque equation, and I say that net torque about A, point A as suggested here, must be equal to 0. You can consider any point, you will get to the same answer finally. Try it out. Okay, must be equal to 0. Why? Because the problem clearly states that the system is in equilibrium. So this implies, what about x? X is passing through A, so its perpendicular distance will be 0. What about y? It is y into perpendicular distance is 30. Y plus, because this is point A and this is force y, and it is making the rod go anti-clockwise, right? So anti-clockwise according to me, right? So I've taken it as plus. So y into 30. The 6 Newton force will also make it go anti-clockwise according to me. I'm behind the pen, correct? So it will be 6 into its perpendicular distance will be 30 plus 10, which is 40, and the other 6 Newton force which is acting downwards will be on the other sense, right, clockwise. So it will be minus 6 into, this is 40, this is 30, so 40 plus 30 is 70, and this must be equal to 0. So I'll have 30y is equal to, take the other two terms to the RHS, take 6 common, so I'll have a plus 70 minus 40, which is again 30. So this 30 and this 30 cancels out, and you're gonna get y is equal to 6. And since x is equal to y and y is equal to 6, x is also equal to 6. So the values of x and y are, x is equal to 6 Newton and y is equal to 6 Newton. That's the required answer for this particular question. And which is the option that supports our result? Well, it is option D.